Thank you everyone for being here. This is my first MIFA public lecture as the director of the Minnesota Institute for Astrophysics, so I'm very happy that you are all here. I'm a little sad that the weather did not cooperate tonight, and so there won't be a public observing session tonight. But as some of you may know, we have Friday night observing on the roof of the Tate building, so here in campus. And we do it every Friday. And now coming up, there is also Universe in the Park. And this is an activity that is run by our great graduate students, where you can just go to a park in Minnesota. The sky is extremely dark, and it's fantastic. So I highly recommend that you look into that. It's coming up when it's a little warmer in June. So today marks a special day for the MIFA public lectures because it's our 10th anniversary of the lecture. And I'd like to remind you that these lectures, they want to showcase the research that is done in our institute. And so all the faculty that you see, all the presentations that you see are our own, they're given by our own faculty, is the research that goes on in the department. So these are the graduate students, the faculty, the postdocs. It's all done here. So today the lecture is going to be by Professor Ali Sulaiman, who received his PhD in space physics from the Imperial College London in 2016. He then moved to University of Iowa, where he was a research scientist until he joined our department in 2022. So he's very new to Minnesota. Ali is an expert in the solar system. He's an expert in electromagnetic field surrounding a planet in our solar system and their moons. And so today he's going to tell us about a life in the day of outer solar system exploration. Thank you, Ali.
Thank you, Benji. Thank you, Claudia. And thank you, everyone, for being here tonight. I'll just make a slight correction. The slide before said that I'm an associate professor. I'm actually an assistant professor, unless the reward for giving this talk is tenure. But until then, all right, thank you. So I'm starting with, here is a recent snapshot of Jupiter by the James Webb Space Telescope. And I think that this is really a magnificent image in many regards. We can see lots of high-resolution detail. So for one, the very well-known Great Red Spot, which is about 3 times the size of the Earth. And this also captures the various structures associated with the atmospheric patterns and winds. We can see the belts and the zones and a bunch of vortices and cloud tracks. And also something that's closer to my heart are the auroras, which is the northern and southern lights, and that will be a focus of my talk today. We can also see the diffuse ring here, and one of Jupiter's moons called Amalthea. And this diffuse haze that we see here comes from Io, which is Jupiter's innermost Galilean moon. It's a volcanic world and will be another focus of today's talk. Okay, so I thought, since we're doing a tour of the solar system, I will start with possibly the most well-known and most successful program, which is the Voyager program. These were 2 spacecraft that were launched in the late 1970s in the midst of the space boom. And talking about the right time, this seized an opportunity for planetary alignment. And essentially, once every 175 years, the 4 outer planets, that's Jupiter, Saturn, Uranus, Neptune, are aligned perfectly in such a way that you can send a space probe and pass through each of them, which is exactly what Voyager 2 did. Voyager 1 actually got kicked out of the ecliptic plane, and that was because it had the focus on Titan, and just the way the orbital mechanics worked, it meant that it couldn't go all the way through. But Voyager 2 managed to go through to Uranus, Neptune, and they both keep going to the extent that in the early 2010s, Voyager left the solar system. And really this marks the beginning of Voyager's journey now. So the transit through our solar system is only a fleeting memory for Voyager, because now it begins its odyssey. There's no turning back, but there's also no stopping. And for that reason, those who planned Voyager had the great thought of putting in a golden record, and this was spearheaded by none other than Carl Sagan. And in that record, there are sounds of our world. So songs of humpback whales, sound of a kiss, thunderstorms, Bach, Beethoven, as well as images, and also a note from President Jimmy Carter that reads, "This record represents our hope and our determination and our goodwill in a vast and awesome universe. We are attempting to survive our time so we may live into yours." And in 50,000 years, when the pyramids crumble to sand and the world becomes uninhabitable, Voyager really will be at the beginning of its journey. And who knows what alien eyes will gaze at Voyager and get a hold of this golden record and wonder about us. An interesting trivia I learned last week is Carl Sagan actually wanted to include the Beatles song, "Here Comes the Sun," in the golden record. And the Beatles were on board, but the copyrights are owned by EMI, and they asked for too much money. And Voyager was launched on a tight budget. Okay, and also long before selfies became trendy, Voyager took one, perhaps the most expensive selfie ever. This is a family portrait. As it was leaving the solar system, it looked back and managed to capture Venus, Earth in our humble spot, Jupiter, Saturn, Uranus, and Neptune. Now, what do we mean by leaving the solar system? It depends on how we define the boundary of the solar system. One way to define it is the boundary of the gravitational field of the sun. So the last object that's orbiting the sun could be considered to be the edge of the solar system. But that turns out to be very, very, very far away, and Voyager is still far away from that boundary. In this context here, and in the context of space plasmas, we talk about the solar system as the region in which the sun's magnetic field dominates. So the sun has a magnetic field like the Earth, and that extends far and pervades the entire solar system. And at some point, we have the last magnetic field line of the sun, and that is what Voyager was able to cross. So it is essentially the spacecraft carries a number of instruments that measure charged particles and magnetic fields and waves, and we're able to see that transition from the solar system medium out to the interstellar medium. So looking out, if we were to zoom out, that's what it looks like here. So on this axis, we have distance from the sun being at the origin, and the unit of measurement would be the astronomical unit, which is the average distance between the sun and the Earth. So you can see the Earth sits at 1, and then it's on a logarithmic scale. So each step, we go up by a factor of 10. So Saturn sits at 10 astronomical units, and then Voyager is somewhere beyond 100, where it's crossed the heliopause, which is the last magnetic field line connected to the sun. But you can see we still need to go quite a distance out until we get through the Oort cloud, which is orbiting the sun, until we completely escape the sun's gravitational influence. Okay, so I'll spend quite a bit of time talking about the region in between the sun and the planet. And first, I'll address the question, is space empty? Now, if you look at a volume of 1 cubic centimeter, which is about the volume of a sugar cube, so at sea level, that would contain 2 followed by 19 zeros air particles in that. Okay, so as tenuous as air feels, that's how many particles there are in sugar cubes worth of volume. Now, in space, on the other hand, that same volume has 1 particle. And that actually turns out to be quite significant. So what kind of particles are these in space? They're not air particles. They're something a bit more exotic. And there's a reason why one particle of those per cubic centimeter can be quite significant and can do a lot of things. So if we look at our phases of matter that were taught in school, we know that if we take a solid where all the atoms or the molecules are packed together into a lattice, and we crank up the temperature, then those molecules begin to jiggle, and the heat starts to weaken the bonds between the molecules, or the bonds between the atoms, to a point when the bonds are weak enough such that these atoms can slide past one another. We then get a fluid, and then if we further crank up the temperature, those bonds completely break, and then those atoms and molecules are free from one another, and they're about to move about great distances and great speeds. But what if we increase the temperature even further? Now, increasing the temperature will weaken the bonds between atoms, but if you further increase the temperature, then the bonds within atoms begin to weaken and break. So here is an example of an atom, a simplified sketch. So this is a hydrogen atom. We have one electron that's orbiting around a proton in the nucleus. And then once that heat is added, there's extra energy added into it, then the electron ceases to be bounded by the proton's electrostatic force. So whereas in a gas you'd have these molecules, although they're moving kind of almost freely past one another, the constituents of those atoms are bound together, but in a plasma, they break apart completely. And so effectively, the protons and the electrons move as two distinct fluids. And that means now we have charges. We have charged particles, so they're electrically conducting, they can carry currents, and they can also carry magnetic fields with them as well, which air can't. Air can't see magnetic fields, and air can't carry currents. So interesting things begin to happen. And this fourth state of matter is called plasmas. And although they occur very rarely at Earth, I mean, you can create them in a lab, but only during sort of short, bursty or sporadic events we can have plasmas occurring, such as when there's lightning. The Earth is predominantly made up of solid liquids and gas. But once you go out to space, so here's a picture of what's out there, stars and galaxies and comet tails and supernova remnants. Over 99% of space, or 99% of the visible universe, is made up of plasma. So it's absolutely everywhere, and we can't get away from it. So starting from the sun, our sun itself is a big ball of plasma that's fast rotating. It has its own magnetic field, and it's far from quiet. So especially now, depending on the solar cycle, you get modulations in the sun activity. So here's an example of various active regions in the sun where plasmas and magnetic fields emerge. And we can actually get to see them through imagery. This image was taken by the New Star telescope. So magnetic fields are invisible to the naked eye, but since these plasmas are locked into the magnetic fields, we can sort of track those filamentations, these hairy structures out here, which are most prominent, for example, during a solar eclipse. Now, what about the space between the sun and planets? That's also filled with plasmas. And essentially, the sun, given that it's a ball of plasma that's high pressure, and you can think of interplanetary space as being a region of almost a vacuum, you now have a pressure gradient that acts to pull away or tear apart the plasma from the sun, and that plasma then blows off and pervades the solar system and interacts with each and every planet on the way, and this is called the solar wind. So the solar wind blows off from the sun, and because it's electrically conducting, it also carries with it the sun's magnetic field. And here, so other than maybe what we're more familiar with, which is the gravitation interaction between the sun and the earth, which causes the Earth to orbit the sun, or maybe the light that's coming from the sun, solar radiation. This is actually a physical connection between the sun and the Earth. You get a wind that's blowing of charged particles. They travel about 400 kilometers per second, and they continuously impinge the Earth's magnetic field. So a bit about the Earth's magnetic field: it extends far beyond the Earth's surface, and that magnetic field has a pressure associated with it that's strong enough to stand off the solar wind at some distance away, about 15 times the Earth's radius. And this bubble here of the Earth's magnetic field that carves out the immediate neighborhood is called the magnetosphere. So once you have the solar wind continuously impinging on that magnetosphere, interesting things happen at the boundary, and those charged particles then travel along the Earth's magnetic field lines. So those field lines act as conduits, and they carry currents and funnel them into the polar region, and those charged particles crash into the atmosphere, and the energy comes out as the form of an auroral emission, the northern and southern lights. Now, as you can see, the Earth and the sun are intimately tied together, and the solar wind is pretty much driven by the sun. So one would expect that when you go farther out, when the sun plays a more limited role, just by virtue of being much farther away, that perhaps the auroras won't be as bright, but it turns out that the outer planets have even more powerful auroras that to some extent look a lot like Earth's auroras, but the sun can't really explain everything because they're so far out. So here's some images. So the top row is from Earth-based telescopes. So we have the ALMA telescope in the infrared. Here's the Hubble telescope in the ultraviolet. And then in high resolution, we have spacecraft images. This is from the recent the ongoing Juno mission. This was taken about a few years ago in the infrared. And this is in the ultraviolet of Saturn. And then over here is Uranus, taken by the only spacecraft to get close to it, which is Voyager 2. And you can see that Jupiter and Saturn have this sort of classic ring of light that's encircling the pole, like the Earth. But in Uranus, it's a bit of a mess. It's all sort of, you have these patchy blobs around. And that's a whole different kettle of fish as to why the Uranus auroral morphology looks like that. Now, to give a sense of scale, so here we have 4 magnetized planets. So not all planets have magnetic fields. For example, Venus doesn't. Mars has crustal fields. But Mercury, Earth, Jupiter, Saturn, as well as Uranus and Neptune have permanent magnetic fields because they have a dynamo in their interior. Now, if we were to start at Mercury, Mercury has a rather weak magnetic field. And you can pretty much tell because the magnetosphere stands off the solar wind at quite a short distance from its surface. Actually, often the solar wind has been found to impinge directly on its surface. Now, you could box up the entire magnetosphere of Mercury, and that would fit our planet Earth, the rocky kind of surface of the Earth. And you can see that the Earth's magnetic field is far stronger in proportion as well. And that's because the magnetopause here, which is the boundary of the magnetosphere, that stands off the solar wind at around 15 times its radius. That's how much pressure it's exerting against that solar wind. Now, of course, you only get that confinement on the day side. That's why you get a bullet shaped. But on the night side, there's nothing confining it. So it tends to go far back. Now you can box up the entire Earth system here, and you can place it into Saturn. So to give you a sense of how enormous Saturn is, also has a very strong magnetic field, and Saturn's magnetopause stands off the solar wind at about 20-25 times the radius of Saturn. And then you box everything up, and you can go into Jupiter's neighborhood. And Jupiter is absolutely enormous. Its magnetic field is so large that if it were visible to the naked eye, it would be the largest structure in the night sky. So the magnetic field strength is about 23 times that of the Earth, and the magnetic moment is about 20,000 times that of the Earth. It's so large that its magnetopause stands off the solar wind at about 100 times the radius of Jupiter. Not only that, you can see the night side. How far back does this tail go? New units are used here, not Jupiter radii, but astronomical units. So over 4 astronomical units away from Jupiter, that's essentially Saturn. So actually, this tail of Jupiter's magnetic field has been observed to intersect Saturn. That's how large this structure is. Jupiter is also a very fast rotating planet. And as I alluded to earlier, the solar wind doesn't play much of a role because it's about 5 times far away from the sun than Earth is. So it doesn't really acquire much of its plasma from the solar wind, but it does have its own little plasma generator, and that's its moon Io, which releases about 1 ton per second of volcanic material that eventually turns into plasma. So here's a 3D impression of Jupiter's magnetosphere. So again, the fields are so strong and the magnetosphere is so vast such that the orbits of all of the Galilean moons, so Io, Europa, Ganymede, Callisto, are all permanently immersed in Jupiter's magnetic field. And that's unlike our moon. Our moon spends most of its time outside Earth's magnetic field, and every now and again maybe makes a very quick excursion into the magnetic field. But these, they have nowhere to go. They're always experiencing Jupiter's magnetic field. Now, Io, the innermost moon, is arguably the most hostile environment in the solar system. I'll show some images later. There are lots of volcanoes scattered around, and it is continuously spewing out volcanic material in the form of sulfur dioxide. And over time, those get ionized into sulfur and oxygen and molecular sulfate atoms, ions, I mean. And once they become ionized, they then experience the magnetic field of Jupiter. They begin to feel that magnetic field rotating past them. They become entrained in them, and they essentially give rise to the currents that eventually power Jupiter's auroras. So the auroras of Jupiter are generated entirely internal to its system and pretty much very little to do with the external solar wind. There is some role for the solar wind, but not as dominant as the internal processes that are taking place there. So it's kind of like a solar system in its own right. Now, the other moons are also very interesting. Europa contains a subsurface salty ocean, and there's lots of plasmas around Europa in the form of water group ions. So there's hydrogen ions, molecular hydrogen ions, as well as oxygen. And then you go a bit further out, you get to Ganymede. Ganymede's another unique moon. It can almost qualify as a planet because it's the largest moon in the solar system, but it's larger than Mercury, and it's also the only moon that we know of that has its own permanent magnetic field. So you kind of have like a Russian dolls configuration here. You have a magnetosphere of Ganymede within the magnetosphere of Jupiter, within the magnetosphere of the Sun, which is the heliosphere. And then you go far out, Callisto as well is an interesting world. So they're all very fascinating places. I'll talk a little bit more about them, but they're also unique in their own right. Okay, so why do we care about the auroras? Why do I spend time researching the auroras? So for one, the auroras essentially give essential context to understand the dynamics of the magnetosphere and the atmosphere. So even before spacecraft got close to Jupiter, we could measure auroral signatures from radio emissions that were coming from Jupiter, and that told us we could directly infer that Jupiter had a magnetic field. And there's now a movement to search for radio signals, auroral radio signals from exoplanets, because that's a nice and easy way to infer that those planets have a magnetic field, for one. And then by getting a sense of what the rotation period of these radio signals are, you can then get an understanding of how long a day is in those planets. But beyond that, if we're to look at detailed images like this taken by the Hubble Space Telescope, you can see that we have a mosaic of what's going on in Jupiter's magnetosphere. So maybe if I go back, I can show exactly what's going on. Everything in Jupiter's magnetosphere, you can map it along the field line and onto its pole, and it will have an imprint on that pole. So for example, you look at Io in its orbit, that's a magnetic field line that's threading Io. You can map it all the way, and you can find Io's footprint right here. And same with the other moons as well. And then also everything that's going on here tells you something about the dynamics, the environment around Jupiter's magnetosphere. So I mean, this maps out to regions of hundreds and thousands of miles. So you can sit and look at an image over time and get a sense of what the dynamics and the structure is of Jupiter's magnetosphere. The second is maybe not so obvious why the auroras are very important, is because of the so-called energy crisis. Now, as I mentioned earlier, these outer planets, they're so far away from the sun. So Jupiter is at 5 AU, which means it intercepts 1/25th of the solar radiation that the Earth does. Saturn's at 10 AU, so it intercepts 1/100th of the solar radiation. That's the one of R squared law. But their upper atmospheres actually have been measured to be very hot. And you can't explain those temperatures from solar radiation alone. So here were measurements made by a probe dropped by the Galileo spacecraft, which was the first orbiter around Jupiter. And it was making measurements of the temperature of the atmosphere on the x-axis against altitude. And you can see that once you get to the ionosphere, which is the upper atmosphere that is ionized, these measured temperatures are far higher than what you would expect from solar radiation alone. If that were the sole cause of heating, that would not be able to bridge that gap. So to put in numbers, Jupiter's atmosphere is about 700 Kelvin, and that's 4.5 times hotter than what solar radiation models would predict. And the same exists in planets such as Saturn, Uranus, and Neptune, 2.5, 5.8, 4.5 times hotter. So what can explain that gap? Turns out it's the auroras. They're so powerful that they dump an enormous amount of energy into the poles of those planets. If you were to look at Jupiter, we're looking down at the North Pole, and this is color-coded by temperature. So the whiter here, the hotter it is, and you can see the polar regions are exactly where you would see the hottest or the highest temperatures. And then there's a smooth gradient as you go equatorward, so that heat is being dumped into the poles and they get transported towards the equator. So if you want to understand anything about the atmosphere, the Great Red Spot, circulation, dynamics, you need to understand what's going on with the aurora, because that's the main source of heat. Now, in the outer solar system, we have one mission there and a few on the way. And the mission that's there now is the Juno spacecraft. It's the second orbiter around Jupiter, but the first polar orbiter. So for the first time, it's been giving us access to the heart of the polar regions and the auroras. And mounted onto Juno, we have a number of instruments that make both remote measurements, so they take images. There's a visible camera called JunoCam, images in the infrared, images in wavelength, as well as in situ measurements. So these are local measurements of charged particles, electric and magnetic fields. And here's a sketch that shows what Juno's trajectory is like going over the poles. So it goes straight over the North Pole, and it traverses magnetic field lines that are directly connected to the aurora. And as I mentioned earlier, these field lines, they act like conduits. So they carry those currents. That's where the particles are accelerated, and they travel along those field lines into the aurora. So Juno is able to make critical measurements of charged particles and the electromagnetic fields that fuel these particles and accelerate them into the aurora. And this is the entire mission of Juno. This is what the trajectory looks like. So we start from PJ01, that's Perijove 1, that's the first flyby around Jupiter. And essentially it comes in from the North Pole whizzes past, it goes from pole to pole in about 2 hours, and then it has a very, very large apogee. It's a very highly elliptical orbit and polar, so it would come round again and then go this way, such that the orbital plane is evolving in this sense, in the counterclockwise sense. And that basically enables two things. One is you can see that over time, we get excellent altitudinal coverage over the North Pole. Okay, so we can get full access to the acceleration region, what's happening before, what's happening during, what's happening after. But then also as it comes round, you can see that Juno crosses Jupiter's equator at distances that are closer and closer to Jupiter. And this has opened up pathways for flybys of these moons. So in 2021, Juno flew past Ganymede, late 2022, past Europa, and we were lucky to have 2 flybys of Io. The most recent one was in February. And this orbital evolution kind of comes for free. That's because Jupiter isn't a perfect sphere. It's bulged at the equator and flattened at the poles, and that inhomogeneity in the gravitational field leads to the orbits changing over time. Now, I won't go through this in detail, but this is just to give you an idea of where we are with understanding Jupiter's aurora. There are various different zones, and the acceleration mechanism for each zone is very different. But this is a catalog, if you like, of all the various waves, electromagnetic fields, and charged particles that participate in powering the aurora. And as it is with space missions, they tend to answer your questions, but then they breed even more questions. So going forward, we'd like to understand what the interplay is between all of these microphysical signatures, and then how do these processes account for the brightness below? Okay, how do we get to generate such powerful auroras? So moving a bit away from plasma's electric magnetic field, Juno has other science objectives. And one of them is to constrain the interior and the distribution of mass within Jupiter. And the way it does that is actually using a very clever approach where just by using radio signals that are beaming from Jupiter all the way to Earth, you essentially have the blue line here. That's the predicted orbit of Juno. Okay, it's coming in from the north and passing down into the south. But in reality, there are wiggles associated with the orbit. And the reason being because the distribution of mass is not uniform. There are some latitudes where there is more mass and they will exert a greater pull on Juno. So Juno will get a bit closer. And then some parts where there's not that much mass and they will exert less of a pull. And so Juno will wiggle the other way. And all throughout, Juno is beaming radio waves back on Earth, and then you can then see the Doppler shift in the wavelength of these radio waves. So the wavelength gets stretched or squeezed depending on whether Juno is pulled a little bit towards Jupiter or pushed away from Jupiter a little bit. So kind of like an ambulance or a train passing by. You hear 2 different pitches, whether it's coming towards you or moving away from you. That's exactly what's going on here. Now, there are also other instruments that can look into the atmosphere, but also beneath the atmosphere of Jupiter. So here we have measurements from the microwave radiometer, which has 6 different channels that have 6 different frequencies. And you can think of each frequency gives you a view of one layer of the onion. So here's an image of the Great Red Spot. That's from the visible camera. So James Webb Space Telescope saw that. But then if you consider the various frequencies of microwave, you can look at layers that are deeper and deeper. And what this discovered that the Great Red Spot is surprisingly deep, so about 300 kilometers deep. So that's far, far, far greater, even in proportion compared to, say, the hurricanes and the cyclones that we have at Earth, which are mostly superficial. And then the atmospheric circulation pattern at Jupiter has also been constrained. So at Earth, for example, we have circulation cells, so Hadley cells, for example, which are between the equator and the tropics. So at Earth, for each hemisphere, there are 3 atmospheric cells. And they go up to actually a few kilometers, I think all the way up to the tropopause. But at Jupiter, you can see for the same number of degrees in latitude, it is far denser when it comes to atmospheric cells. So the atmosphere of Jupiter is far more dynamic. And of course, the aurora, given that it dumps so much heat into it, is a main driver of that, in addition to Jupiter's very fast rotation as well. Now, this was the very first flyby of one of the Galilean moons. This was Ganymede back in June 2021. And this is an image captured by the Juno cam in very high resolution. And what's really fantastic is that images can be compared with those of previous spacecraft to look for how the surface evolves. As I mentioned earlier, Ganymede is the only moon that we know of that has its own internal magnetic field. But in addition to that, it has a subsurface ocean, and it's believed to harbor more water than all of our oceans combined as well. And as a result as well, not shown here, Ganymede also has auroras, northern and southern poles there, because of its magnetic field. Then here's Europa, a year and a few months later. Europa is also very interesting because it has a subsurface ocean, and I'll talk about how we know there are subsurface oceans there. So confident that there's actually a mission being sent all the way to Europa to characterize the ocean in further detail. And then Io, 2 flybys, one in December 2023 and one in 2024. And you can see it's a very tortured world, lots of volcanoes scattered around. And those volcanoes are much higher than Everest in absolute terms. Okay, so not just normalized to Io's radius. They are extremely, extremely high structures that are coming out of the surface and continuously blowing up. And we were lucky that during the second flyby, you can see that there's a double plume here, capturing volcanic eruption. Now, even better, in the infrared, you can see all the lava and lots of lava lakes around. So we're not going there anytime soon, and for good reason. Okay, so why do we care about the moon? As I mentioned earlier, well, for one, we know that there's liquid water there. And that actually starts to bring up conversations about habitability and the conditions for life. So one thing we know is that in order for life to be supported in an environment, we need liquid water, we need hydrocarbons, and we need energy. And all of these are found in Jupiter's moons as well as Saturn's moons as well. So there are measurements as well of hydrocarbons, methane, for example, and potentially even longer chains. Now, for long it was thought if we were to look at exoplanets far out, we would only have to focus on the so-called Goldilocks zone. Okay? So planets that are orbiting their host star, not too close, because otherwise water would evaporate, would become steam, and not too far, because the oceans would be frozen. So you'd want somewhere in between, like the Earth is in the Goldilocks zone, where water exists as liquid on the surface. But now we learn that liquid water need not exist on the surface. We can have lots of it beneath the surface. And those are in liquid form, and they're kept liquid due to the tidal forces, because these moons are orbiting Jupiter's enormous magnetic field. They have an eccentricity associated with it, so they're not perfectly circular. Sometimes they're a little bit closer to Jupiter, sometimes they're a little bit farther apart, and that push-pull leads to friction, tidal heating, and that's enough. With inclusion of antifreeze, it's enough to keep the water liquid. So that really has ushered in a new era of exploration, that we can look pretty much anywhere, and we don't even have to limit it to planets as well if we want to search for the conditions for life. Now, how do we know that there are oceans if they're beneath the surface? So it turns out that this was done from magnetic field measurements. And that is because these oceans, the fact that they're salty means that they're conductive. And as I showed earlier, these moons are orbiting around Jupiter. They're continuously exposed to Jupiter's magnetic field. And Maxwell's equations tell us that if you have a time-varying magnetic field with a conductor, that's going to give rise to an electromotive force that will drive a current, and those currents will induce a secondary magnetic field. Okay? So essentially, if you're measuring the magnetic field past the moon, you would expect to see a certain number, but when you see wiggles there, that hints into something that's being perturbing or adding into the magnetic field. Now, this is very challenging because if you're measuring the magnetic field, you're measuring a vector sum of different magnetic fields. So for example, you're measuring Jupiter's field, you're measuring magnetic fields as a result of currents that are flowing in Jupiter's magnetic field. For the case of Ganymede, it's even more complicated because Ganymede has a magnetic field of its own, and there are currents that are associated with Ganymede's magnetic field, and there's also an ocean. So the trick here is to disentangle all these various magnetic fields and to isolate the one that is associated with the ocean. So here's a visual of what this time-varying magnetic field is like. Now, if you have a moon, suppose it's Io, going around in its orbit, how do you get a time-varying magnetic field if it keeps staying in its orbit and doesn't go anywhere else? Well, it turns out, fortunately, Jupiter's magnetic field is tilted from its rotation axis of about 10 degrees. And so that means every Jupiter rotation, you have a wobble in the magnetic field. So that is your time-varying factor in your magnetic field that results in driving currents through your conductor that will then induce a secondary magnetic field that can be measured. Now, moving on into the Saturn system. So Saturn's well known for its rings, but Saturn also has very, very interesting moons. There are two very well-known moons that I'll talk about today. One of them is Titan, and this is an image taken by this James Webb Space Telescope. Titan actually orbits very, very far away from Saturn, actually at the boundary of its magnetic field. And Titan has a very, very thick atmosphere, and it's very hazy as well because it contains tholins. And that's also fortunate because that means we can send a rotorcraft there and you can glide and you can fly through the atmosphere because it's thick enough. And it turns out that there's going to be a mission on the way there called Dragonfly. So a bit about the Cassini mission, which was the first and only orbiter around Saturn. This launched in 1997 from the Kennedy Space Center. And it took a 7-year voyage across the solar system to get there. And the way these things work, from the beauty of orbital mechanics, it turns out if it were to go all the way to Saturn directly from Earth, that would have taken about 20 years. But doing a series of maneuvers called gravity assists, that meant that Cassini basically flew past the Earth a few times and then went past Venus twice before going through Jupiter all the way to Saturn. And each time it passed Venus or the Earth, it got an extra kick from the conservation of momentum. So the spacecraft got a boost in velocity, but that comes at the cost of the planet slowing down. But because they have vastly different masses, that's a very, very, very small amount. So we don't have to worry about waiting longer for our next birthday. Now, along with Cassini, there was which was a NASA flagship mission. There was, you can see the dome over here. This was a European-built probe called the Huygens probe, which landed onto the surface of Titan. Now, the problem with Titan is that because it has such a thick, hazy atmosphere, the surface is obscured, so it's very difficult to use various wavelengths to be able to map the surface. So often you need things to get right down to the ground. So here's an image from,
14th,
or a movie, I should say,
with the Earth
from the Huygens probe.
in between the Sun and Saturn, an opposition so perfect that it occurs maybe twice per millennium. Meanwhile, the Huygens probe, quietly entering the Saturnian system, is about to end its 7-year journey. As Huygens approaches, the inner planets cluster around the distant Sun. Saturn appears almost as large as Orion. A few moons are visible as white dots aligned with Saturn's rings, while Titan, its largest moon, is already well resolved. Huygens is destined for Titan, a mysterious world larger than the planet Mercury and shrouded by a thick brownish-orange atmosphere. The details of its surface have never been seen. Huygens' speed increases to near 6 kilometers per second, and Titan's disk quickly obscures our view of Saturn and its more intimate moons. As the probe enters Titan's atmosphere, the heat shield reduces the speed some 15-fold within a few minutes. The main parachute reduces the speed further. 15 minutes later, the smaller stabilizer chute allows a faster descent at first, but slows as Huygens enters the lower
these are real
part
images
of Titan's atmosphere. Huygens is approaching a dark valley between brighter hilly regions. Beyond the hills to the left, 2 dark parallel lines appear, which are later discovered to be part of a vast system of dunes which surrounds the moon. At 21 kilometers altitude, the probe moves through a thin haze layer as seen on the horizon. A bright area near the center top is the glow of Titan's haze illuminated by the sun. A complicated system of drainage channels, some hundreds of meters wide and kilometers long, are seen cut into the hillside. These are probably the result of runoff from methane rain. Stereographic imagery reveals hills to the left to be perhaps a few hundred meters tall, while features in the valley are tens of meters in height. For most of the descent, the probe travels eastward above Titan's surface. However, below 7 kilometers altitude, the motion reverses into a backward westward motion. It reverses again at 1 kilometer altitude, and we move slowly southeastward. Hang on, as Huygens lands on Titan's surface near a water ice outcropping ridge. Another westward-looking view of the descent from 31 kilometers shows the area of Titan over which the probe has just flown. This affords us a good view of the drainage channels and apparent shoreline. More dark lowlands appear and a rough pitted hillside to the left. Spectra of the surface suggested the bright areas are water ice, and the darker areas are a type of hydrocarbon mixture that has never been produced in the laboratory. The small white dot in the lower center part of scene tracks our progress over Titan's surface. We see the reversal in direction at 7 kilometers altitude, and we fly over the ridge near where we will land. As we approach the surface, our perspective brings the topography to life. We see that although there are rivers and a shoreline, the basin is dry. Below, there are distinct signs of erosion which crafted the rugged ridgeline. Huygens sinks into one of these gullies. We experience a relatively soft landing on Titan's surface. The view from the surface reveals an amazingly Earth-like picture of a dry riverbed, with distant hills which are a few meters in height. Some seconds after impact, the shadow of Huygens' parachute drifts across the scene. The heat from the surface science lamp in the probe's skin vaporizes methane from Titan's surface, which is about 180 centigrade degrees below freezing. Near the probe, the ground is littered with water ice rocks and smaller pebbles, which could be made of water ice, or hydrocarbons, or some combination thereof. Although we now know more than ever about this mysterious world, many questions remain unanswered. Where is the vast reservoir of liquid methane necessary to replenish the atmosphere? Where and how often does it rain on Titan? How does the methane get recirculated into the atmosphere? What materials make up the surface? What processes create and shape the hills, dunes, and valleys?
And we'll find out soon, hopefully, because the Dragonfly mission, we have a rotorcraft that will be on its way to Titan, and I think it was formally approved by NASA earlier this week. And I believe the scheduled launch is 2028 with arrival 2032, plus or minus 2 years, which is nothing when you think about the outer planets. Again, you have very thick atmosphere, so you can actually build machines that glide and fly, but also it's smaller than the Earth, so the effects of gravity are not as significant as that for the Earth. So the perfect place to send flying machines. Now the other moon is Enceladus, and this is a very little moon actually scientists knew that Titan was a very interesting moon because Voyager saw that haze, and Carl Sagan took a very deep interest in the moon. But actually, little was known about Enceladus until Cassini got there, and some major discoveries were made. So when the spacecraft flew past the moon, the magnetic field was seen to wiggle, and that wasn't expected because if the moon, which was thought to be an inert body like our moon, if you had a magnetic field go past it, then nothing would happen to the magnetic field. So you think about wiggling a bar magnet and a block of wood, they don't really talk to one another. But it turns out the magnetic fields were perturbing, and subsequent flybys were made and the cameras were turned on, and what was discovered were water plumes that were being ejected from the south pole of Enceladus. And when the infrared looked at the south pole, they found these tiger stripes, so basically heat patterns that essentially gave clues of what's coming in from the interior. There was geological activity occurring at the interior of Enceladus. There's an internal heat source at Enceladus, and there's a continuous ejection of water that's emanating from the South Pole. Now, this is actually so significant that I'm going to go back to this image, and one thing that you may or may not have noticed is the E-ring, which is Saturn's largest ring. And the source of E-ring is this little tiny engine right here in Enceladus that is continuously releasing water to the extent that you have this very, very, very diffuse ring that's extending all the way far out to Rhea and beyond. And actually the clue is here, you can see the peak is in the orbit of Enceladus, indicating that Enceladus is the source of the E-ring. Some mass spectrometry was conducted as well to find that there were various hydrocarbons, but only simple hydrocarbons were reported, and that's just because of the basic technology of the instrument at the time. And so there are future proposals to go back to Enceladus with more sophisticated mass spectrometers that can measure long-chain aliphatic hydrocarbons, aromatics, as well as distinguish between chirality. So that's right-handed versus left-handed molecules. It turns out that life seems to always have a preference when it comes to chiral molecules, always picking the left-hand molecules. So that can be a good indicator of potential habitability there. Now, a lot of that water that comes out of Enceladus gets ionized and becomes plasmas and interacts with the magnetic field, and that gets involved in driving the auroras of Saturn as well. So Enceladus, like the moons of Jupiter, Io and Europa and Ganymede, also has its own spot on Saturn's northern and southern pole as well. And this interaction is actually so powerful that when Cassini flew past very close to Saturn, you can see we're over 100,000 miles away from Enceladus, but we are on a magnetic field line that is connected all the way to Enceladus. Electromagnetic field disturbances were measured. And here's an audio file that shifts the frequency down to the audible range and compresses it in time, so we can get an audible feel of what that sounds like. That's the sound of Enceladus, sound of tiny Enceladus, 100,000 miles away, no different to a toddler. And you can actually go and watch this video. It's on YouTube, and I find actually what's more interesting are the comments that people have about this. Okay, so I'll just spend the last few minutes talking about the future. The future is bright for outer planet exploration, and really it's mostly surrounded around the moons because of all these major discoveries that have been made in the last 2 or 3 decades. So for one, there's the European flagship, which is the Jupiter Icy Moons Explorer, or JUICE, that launched last year and will arrive at Jupiter in 2031, and it will be the first spacecraft to orbit a moon other than our own, and that would be Ganymede, in 2032. And as I mentioned earlier, if you're trying to characterize the interior, you have to separate all the different contributions of the magnetic field. And in order to do that, you need something to orbit around Ganymede to separate spatial from temporal variability. Okay, so in order to fully characterize the ocean, you need to peel off Jupiter's magnetic field and you need to peel off Ganymede's magnetic field. And only an orbiter will be able to do that. Roughly around the same time, actually this will be the first time we'll have 2 orbiters around Jupiter at the same time, which means we can make multi-point measurement for the first time. This is a NASA mission, the Europa Clipper mission. Its focus will be on Europa. It won't orbit, but it will conduct a series of flybys around Europa in order to fully characterize the surface and the interior, and with sort of instruments that are next generation that can perform high resolution, high fidelity measurements. This is due to launch later this year, so watch this space, and it will arrive at Jupiter 2030. And then even beyond, if there's any more patience one can find in this field, we hope to get to Uranus and send the very first orbiter there, of course. The only spacecraft that's to go past Uranus was Voyager 2 and send those patchy images. But actually there's a number of things about Uranus that Voyager discovered that were very surprising. So for one, in terms of its magnetic field, you can see, if you can get your head around this, the planet has an obliquity that's over 90 degrees. Okay, so it's kind of tumbled in this direction. The sun is coming from that direction, so you can see here. So when you look at Uranus, you can directly see the face of the rings, and the southern pole, for example, in this season is in complete darkness for a very long period of time. Now, in addition to that, the magnetic field is tilted by a very large angle from the rotation axis, and it is also shifted from the center of the planet. So try and imagine visually, if you rotate the system about this axis, you have a very tumbling magnetic field, and for that region, there isn't one spot where you get all of the auroral particles crashing into. They could be anywhere. You could have the auroras in the equator, anywhere, and that's just because the whole magnetic field is a mess. It's on its side and it's continuously tumbling as well. It turns out the moons as well are also very interesting. They're very large, and really now there's reason to believe that they have oceans. That turns out to be possibly more likely than not. For example, I mean, if you look at Enceladus, for example, it's a very, very tiny moon, and that has an ocean. So there's no reason to believe why even larger moons may not have even more interesting things there. Now, Uranus was recommended in the latest planetary science decadal survey. It's been given the highest priority for the next NASA flagship, and planning for that is underway. So at least for me, and just the nature of how the work in the outer solar system. When I joined the field, I worked on Cassini data that was being planned in the 80s. I joined the field in the early 2010s. A lot of the people who put their blood, sweat, and tears to make Cassini happen were not there anymore, and I enjoyed the fruits of their labor. And now I feel, working on Uranus, it's my time to give back, because by the time we have an orbiter around Uranus, I'll maybe be in a retirement home somewhere. So great. On that note, and have the future generation enjoy the data. So thank you all.
Questions for our speaker?
Thank you very much. In regard to Uranus, is the different nature of its magnetic fields and rotational aspects probably due to an impact sometime in the past?
That is a potential explanation, yes. But it's still up in the air.
Thank you. I noticed in the for the Europa Clipper mission, a natural question is why would it not orbit Europa? I have a potential answer to that. I'm just curious what your answer is.
Yes, that's because of planetary protection reasons. So when sending out spacecraft to the outer solar system, NASA needs to demonstrate that these spacecraft won't crash into these potential habitable worlds and contaminate them. And the probability has to be better than, I think, 1 in 10,000. Now, if it were to orbit Europa Clipper, then the end of the mission means it would have to crash into Europa Clipper, and that would violate planetary protection. The only way out of it would be to deorbit Europa Clipper, but that would need a lot of resources and propellant in order to do that. So that's just not feasible.
Thank you.
Okay, so I have two questions. One is, when the Earth's magnetic field flips, what impact does that have on the solar winds and the interaction? And my second question is, what role is artificial intelligence now playing in the analysis and the future of the science?
Yeah, so I'll answer your second question first. It's helping with data analysis. I mean, especially in the outer planet mission, these missions go on for over a decade. There's an enormous treasure trove of data. Never enough time, never enough people to analyze that data. So now artificial intelligence is helping to sift through the data and looking for certain patterns, or at least guiding us to efficiently look at what data needs to be analyzed. Back to your first question, you said the Earth's magnetic field rotating. Did you mean the sun's?
Doesn't the Earth's polarity switch?
It does, but over an extremely long time scale.
Yeah, isn't it like 26,000 years? Or
yeah, something like that.
But when it does occur, what will happen with the sun's interaction with the solar winds to the Earth's magnetic field?
So I guess the easy answer is we haven't been here long enough to observe that change, but I can speculate. I'd have to go back. Okay, so here's the Earth's magnetic field. It goes from south to north, okay? And that's Jupiter and Saturn, by the way, that goes in the reverse direction from north to south. Now, that direction of the magnetic field is important for this interaction because when the conditions are right, you can get a process called magnetic reconnection. That's when the sun's magnetic field connects with the Earth's magnetic field. And when that happens, the boundary opens up, there's a cavity, and solar wind plasma is able to access the Earth. Now, because the Earth's magnetic field points from south to north, that means in the magnetopause, the field line is pointing northward. So in order to get magnetic reconnection, the best angle orientation you need from the sun is a southward magnetic field to do that, because south will merge with north and it will open up the cavity. Now I imagine if the Earth's magnetic field were to be flipped, then the reverse would be true. So you would need a northward pointing solar magnetic field in order to have the best chance of getting magnetic reconnection. But then what happens in between? Suppose you could have the poles of the Earth that's facing towards the sun here. I'm imagining if it's flipping, you're going to get at some point the cusps are pointing towards the sun, then that's just open access to the solar wind. And that's what Uranus is. So if you If you look at Uranus, it is pointing towards the Earth, and there's times where you can have the cusp that's directly into the solar wind, and for Neptune as well, actually, especially for Neptune. And the locations of your auroras would be different. You know, you'd maybe fly to Africa to see the equatorial lights in that case.
This is a great talk. Thanks very much. I'm very interested in what SpaceX is doing with their latest rockets that theoretically will put 100 tons, into orbit at a very low cost. And I'm just wondering if that's going to affect the amount of science that can get done. Because when I look at the probes that are launched now, they seem to be very small. And obviously, once they get into orbit, or they, get past the orbit of the Earth, it takes a lot of fuel.
Yes.
To get much further. So will there be a big impact if SpaceX can actually pull this off on science?
Oh, absolutely. Yeah. I mean, the bigger the rocket, the bigger the spacecraft, the more instruments we can have. So that's a limiting factor there. If you want to go far out into the solar system, and we want to get there soon, we need a very big rocket in order to do that. But if you're building a very spacecraft that has a Christmas tree with lots of instruments there, then you have that trade-off. So I think it's very interesting that private industry now are throwing their hats in, and coming up with new innovative ideas, being very creative. Because yes, if we want to go farther out, we're going to definitely need bigger rockets. Yeah, and of course, cost is a big thing as well. So bringing in the private industry can potentially bring costs down as well.
Yeah, thanks for the lecture. Up here, in the same context that you described the deorbiting of the Europa Clipper, can you explain what's going to happen to the spacecraft going around Ganymede?
Going around Ganymede, yes.
Yeah.
So
how you can deorbit?
Yes, no, actually, it will crash into Ganymede. For reasons that I don't know too well, the planetary protection requirements for Ganymede are not as stringent as for Europa. Yeah. So you can interpret that as Europa is seen as maybe a better candidate for probiotic conditions than Ganymede. Yeah, but there's also something to do as well with how thick the crust is as well. So if basically nothing essentially can exist on the surface. So even for Europa, Europa is immersed in Jupiter's radiation belts, which is being continuously showered with very, very high energy particles. And these can degrade any biosignatures. So the likelihood to find anything that can support life would come from the interior. Now, Europa is believed to have quite a thin crust. And by extension, I think for Ganymede, the oceans are quite safe from any collisions. If anything falls onto the surface, then there might not be any significant penetration that could cause contamination. So the requirements for planetary protection are much more stringent for Europa than Ganymede. And for that reason, we can send our orbiter around Ganymede and it will crash into the surface.
I don't feel you ask it. I'm shy. Thank you very much for a great lecture. I really learned all the details of
Thank you.
What I did not know before. And I'm very curious because your title is Alive in the Day of Outer Solar System Exploration. If we were to find life in one of the moons, how would it look like? Is it a singular cell or how would it look like? I'm very curious.
Yeah.
Thank you.
That's a great question. I don't think we know the answer to it. I guess we can get philosophical about, what is life? if you ask an evolutionary biologist, they will say, the point from which you get from chemistry to biology is when you have self-replication of a compound. So it could be something as simple as that, finding a compound that can self-replicate, or it could be something as complex as, single-cell organism, although I imagine that is very difficult to detect as well. We're also limited by the technology we have. As I mentioned, it's hard enough measuring long-chain aliphatic and aromatic compounds. It's also hard enough measuring chirality. But taking the limitations of our observations, what could life look like? Well, maybe not. It's maybe not intelligent, because maybe they would have seen our space probes flying by, in the last 50, 60 years. But if not, then, it could be something of the order of bacterial. And that is assuming that that's life as we know it, sort of carbon-based life. Can you have other forms of life where the building blocks of life are a little bit different to what we're familiar with? Maybe. Yeah. So I think the short answer is I don't know what life would look like. But we do know actually at Earth that life exists in environments that are actually very, very hostile as well. I'm trying to remember the name of the lake in Russia, Lake Vostok, I think. Sort of deep down, far away from sources of oxygen, you can have life, even in volcanic regions as well. So yeah, could be life as we know it, could be something else.
Hello, I was just curious, from the standpoint of habitability, is a stronger magnetosphere always better than a weaker one, or is having one always better than not having one?
Yeah, so having a magnetic field helps a lot. So at least for Earth, the magnetic field acts as a barrier to the solar wind. So yes, to zeroth order, it helps a lot. But then also, magnetic fields can lead to atmospheric loss as well. So it depends on the timescales of life that you're interested in. But to zeroth order, like on the Earth, the magnetic field helps us because it shields us from the solar wind, which are energetic particles coming from the sun, and deflects them out of the way. Now for Jupiter's moons, those are all immersed in Jupiter's magnetic field. But then again, there's another problem there, and that's because Jupiter has radiation belts because of its magnetic field. So the surfaces of those moons are showered with very high energy particles. So that's a situation where magnetic fields don't help. Yeah.
Thank you for the lecture. The graphics and the slides were beautiful. Can you give us a little bit of a rundown of the moons on Uranus? We hear a lot about the other moons, but these I'm not as familiar with.
Yeah, I mean,
and about the potential for life too on those.
Yeah, I mean, we know very, very, very little about them. Almost nothing. A lot of the science is done from space telescope observations, and since those are very far away, the resolutions are very low. But I think given that we know that they're moons and their sheer size and what we know about Jupiter's and Saturn's moon, they're suspected to be interesting targets. But we won't really know until we get there. Yeah.
Hi, I'm sure this is an easy question, but I was wondering regarding planetary protections, is the Earth included in that, or are the protections stricter in space?
Well, whenever I turn on the news, it seems not. No, I mean, things fall on Earth all the time from space. I mean, there's planetary protection to the extent that if you were to launch something into space and it were to fall back, you want to make it fall over the ocean rather over a city. So in that regard, yes. But planetary protection typically covers planets in the solar and moons as well. So environments beyond the Earth that could potentially support life. Yeah. I mean, over here, we have to mix in geopolitics and, many other things that it's a whole different department that takes care of that. Yeah.
I wanted to mention that in the cards that you got when you came in, there is also the option for you to add your favorite next subject that you want to hear about. So we are planning the next MIFA lecture for next year, as well as the next Kaufmanis lecture, where we are going to bring in a grain scientist from outside the United States or Europe. And so if there is something that you want to hear about and you're very passionate about, just fill in the form and drop it with the graduate students that are helping outside or in the box outside. Thank you very much for being here. And thank you, Ali, for the talk.
Thank you. Thank you.